In this video, we're going to talk about what is conservation of momentum and when can I use it to make predictions about a scenario or to better understand a scenario to determine an object's mass, determine its final velocity, etc. Okay, conservation of momentum. Conservation of momentum says, here it is, P system equals P system prime. Okay, let's talk about this little tick mark here. That we say prime and it means after. And if there's no prime, like on the left side here, that just means before. So conservation momentum says essentially that take a system of objects at some point in time. Then at some later point in time, under certain circumstances, the momentum of that system will still be the same. Now, usually the before and after is separated by some kind of an event. We've got two things coming together and smacking together. In theory, you could have many things smacking together. Typically, we're only going to be involving two objects, but it could be 3, 4, 5. It could be 100. Or there's an explosion, and it doesn't mean always like, oh, something exploding. It just means two things or more things together were initially joined together and then they break apart. Now, the word system is going to be very important in this case, and it just means your collection of objects. And I think over time we'll get a better understanding what that means. But for just now, it just means you've got two rail cars coming together. Well, those two rail cars might lump them together and consider them to be a system. Maybe you've got two ice skaters, two roller skaters, like there was in that one assignment, the father and the daughter. Well, we might lump the father and the daughter together and think of them as a system of objects. More on that later. But that's what conservation of momentum says, is that under certain circumstances, the momentum of a system will not change. So what are the requirements for us to say that? Okay, and here it is. Here's what it is. Basically, it says, hey, the momentum of your system will not change if we can make the following statement, that the sum of all the external forces must be 0. Now, in determining if the sum of all the external forces is 0, it's helpful to think about your system. And our system of objects can come into two flavors, we'll say. You have a closed system, and you can have an open system. A closed system is one in which there are no external interactions. So think about, suppose that you had two objects let's suppose we had three objects, 1, 2, and 3, and they're all doing whatever they're doing. Maybe they're moving in different directions. It doesn't matter at this point. Well, we would think about lumping these three objects together, not like physically connecting them, but just mentally, okay, there's my system. And what you're going to ask is, are there anything from the outside pushing or pulling on them? And if there are no outside interactions, then this would be a closed system. In a closed system, there are no external forces. So there are no external, I just said it there, but no external forces. So the momentum in a closed system will always stay constant. So momentum in a closed system will always be conserved. Now let's think about an open system. And a great example of an open system this is going to be interesting, is going to be the example of the father-daughter roller skaters. This is, oh boy, there's D for daughter, I guess. Oh my goodness. Okay, anyway, you know what I'm trying to do here. Oh boy. Okay, there's the daughter, and there's the father. Okay, well, hey, I'm not going to redo this. Okay, so we're going to think about them as not individual objects, but as a system. So this is going to be the father, daughter, system. Okay, now is this an open system or a closed system? Well, if they were in outer space, in deep, deep space, far away from anything else, we would say they're a closed system because there would be no external interactions. There'd be nothing from the outside pushing or pulling on our father-daughter system. But they are not in deep, deep space. They are on, or they're basically at a roller skating rink. So they are on Earth, and they are at a roller skating rink. So there are outside forces. So there are external forces acting on our father-daughter system. So when you have external forces, you have what we call an open system, and then you have to kind of push a little deeper than a closed system. If you determine something's a closed system, then there's no external interactions and momentum will always be conserved. Here, now you're going to go back to, well, there are going to be external forces. So now we're thinking about, is the sum of all those external forces, do they add up to zero? And let's take a look at it. Let's identify. So the earth pulls down on the daughter. The earth pulls down on the father with their respective gravity forces. Okay, well, that's definitely external force. But those aren't the only external forces. We can also recognize that since they're not accelerating in the vertical dimension, that there must be an equivalent normal force coming from the roller rink floor, pushing up respectively on the daughter and the father. And these two, not these two normal forces are equal, no. But the normal force on the daughter is exactly equal in magnitude, opposite in direction to the gravity force on the daughter, and the same is true with the father. So in terms of the vertical dimension, these sets of forces, normal force up and gravity force down, exactly cancel out. They add up to zero. So in the vertical dimension, we can see that the external forces in the vertical dimension add up to zero. So at least in the vertical dimension, we're going to say, yes, absolutely, momentum is conserved because, let me write that down, is the sum of all the forces acting, these would be outside forces acting in the vertical dimension, is zero. What about in the x dimension? Well, there's a reason this problem takes place at a roller skating rink, and that is because we want to, well, not me, the people who came up with this problem said, hey, we don't want friction to be a big deal here. So we're going to say that friction is negligible. So even though there might be some friction acting on the father as she goes rolling to the left, and some friction acting on the father as he goes rolling to the right, we're going to say that the size of that friction force, those friction forces, is too small to worry about. And so, yeah, we're going to say that basically even in the x dimension, that the sum of all the forces, outside forces, adds up to zero because friction is too small to worry about. Friction is close to zero. And that's particularly true if we only look at our father and daughter scenario for a limited amount of time. So if we were to go back and say, okay, let's have our daughter roll 100 meters all the way across this enormous roller rink, then maybe friction acting over a long period of time might not be negligible. So typically in these conservation of momentum problems, we're going to look at, hey, what's going on just before the push off, or and then correspondingly what's happening just after. So our time in these problems is usually very, very limited. So tiny forces acting over a very limited amount of time, we can still treat them as though they are zero. So let me just summarize on that. We can apply conservation of momentum whenever the outside forces, when we can say that the sum of all the external forces adds up to zero. In a closed system, there are absolutely no external interactions. Momentum in a closed system will always be conserved. In an open system, we are going to have outside forces acting on our object. We can still say that momentum is conserved if we can say that the sum of all the outside forces adds up to zero, or, and that would be the case here vertically, normal force, the normal force up is not tiny, and the gravity force down is not tiny. They are not negligible, but they add up to zero. That's the case in the y dimension. In the x dimension, there is no force canceling out the little tiny bit of friction, but we can say that since friction is small, and because we're only going to look at our scenario just before the push-off and just after the push-off, we can say that friction essentially is zero. Or, if it's just if it's a made-up problem, we can just say it's absolutely zero. But even in a real-world situation, if we limit ourselves to a short period of time before and after the collision, then even if there is some friction, we could say, hey, it's too small because the time is limited and it isn't that large. All right, that's it on part 2.